All right, today we're going to do insertion and deletion from the Nguyen-Wong B-tree. Now, you're excited about that? I am actually. This is the same story with this as it was with the Sedgwick's improvement of the LLRB tree to make everything simple. I'm here to tell you that there are many algorithm books that describe the removal from a B tree, and the algorithm is so complex that they don't even give the pseudocode. They just give an outline of how you would do it because it's really complicated. And so the amazing thing, is that we never did. It was so complicated that it was never able for us to actually trace through how to remove from a B tree. But this Nguyen-Wong tree is just amazingly conceptual and easy to see how it works. And the whole idea is that it's the same, and furthermore, it's the same idea as the Sedgwick algorithm, where you go down to either insert or remove. You go down, and then you fix up on the way up. It's the same idea. And it's just really, in fact, it's kind of like a generalization of doing what he did, okay? But it's with B trees. It's with, these general N-way trees, not general N-way trees, but they are with these B trees, which are specific N-way trees. So anyway, insertion and deletion is based on moving data vertically in a tree. So now you see, when we did the red-black trees, we were concerned with propagating the links down. The red links down so that we could, do a removal and whatever. But now what we're going to do is we're actually going to propagate the data. We're going to take data values, and data values are going to be propagated down, and they're going to be lifted up. Do you see what I mean? And they're going to be propagated down and lifted up in a way that maintains those B tree invariants. What will be maintained is the height balance, the order, and the node size restriction. All right, now here is a figure that shows how to lift a value up a tree. So you notice in the upper left-hand corner of this figure we have the node 10, 30, 80, 90, and we have the nodes between 30 and 80, 40, 50, 60, and 70. So you understand that you see that that's ordered. Now, what can you tell me about the height of tree A compared to the height of tree C? The height of tree A compared to the height of tree C. What can you tell me about the height of tree, maybe if I ask enough times, what can you tell me about the height of tree A, little letter A, compared to the height of little letter C?
C is 1 meter.
Is it that way or is it the other way? You know that the children all have to be at the same level, right? So which one has the greater height? Tree A or tree little a or tree little c? You understand that those represent general, that's like the triangle. Those represent general pointers to general trees that we're not showing. Is everybody clear on this?
Well,
so tell me, what must be the height of tree A compared to the height of tree C? Say it again. I don't. If they were the same, then you'd have children at different. The children would not be at the same level. I mean, sorry, the leaves would not all be at the same level. Oh, now this is. I'm glad we're asking this.
Yeah, because it's 1
the height of C has to be 1 less than the height of A because the leaves all have to be at the same level. Now let's make sure we get that we understand that the shape of a B tree. Remember, it's that the leaves are every leaf is at the same level. Are you with me? So we can deduce from that the tree A the height has to be 1 greater than the height of the tree C because their leaves all have to be at the same level. Now, is everybody clear on that? So because you see those little letters, those are just represent, general pointers to general trees that we don't have space to show. Are you with me? So now, how do we lift up a value in a tree? So in the upper left-hand corner of the figure, what we want to do is we want to lift 50 we want to move it from one level to another level. So we want to move it up a level. So look what you do. You split up, and we all know what the split up operation does. Are you with me? So you see the 50 gets split up, and so its left child is the 40 and its right child is the 60 and the 70. Are you with me? And then what happens? And then what do you do with the 50? You splice it in. And see, and it has moved up. Now tell me, what about the height of tree A compared to the height of tree C? It's still what? 1 greater, which is what it should be. All right? And so now do you see that the height that all the levels have been maintained, the order is maintained. Now one thing that might not be maintained is the size restriction on the number of values in the root. Do you see that got bigger? So that particular one we'll have to deal with that as a separate issue. Now, question? So what happens is the code for doing the insertion, the insert and the remove is, I'm giving you the pseudocode of this, and then we're going to go through it on the slide. And this code does this kind of thing. So this is just a preliminary to describing how the insert and remove works. Does that help a little bit? Okay, so then when we splice it in, then the 50 goes up, and the only thing we have to deal with then is the fact that by moving 50 up, the size of the node of the root might exceed the size restriction. Because what is the size restriction, you guys? If the order is n, then how many data values are you allowed in each node? Between floor of n divided by 2 and n. Okay, so it depends on what the order of the tree is, whether that violated the order, that size restriction. All right. Now, so that's how you lift a value up. Now, answer me this: how would you move a value? How would you push a value down, going from 1? How would you push it down? What would you do? In other words, how would you move the 50? If 50 is up here, how would you move the 50 down? Oh, yes, that's exactly. Yes, we do want it to be even with the 40, so that the balance is maintained. Are you with me?
Because if you just split it down, the 40 and 60 and 70 move down.
Oh, yes, but then what would you have to do? But then what could you do?
Up?
Yeah. So look, it's just the opposite. It's the same picture. Look, you guys, get this concept. Look, so it's just the same picture, but the arrows are just going the other way. If you have 50 up here and you want to go, then you just got to do it in this order. But now this one is a little bit tricky. I mean, it's a little bit different because we do have a split down operation that goes from the lower right-hand corner to the middle lower picture, right? We do have a split down, but do you see that we don't have a single operation to go in that direction? In other words, it's going to have to be a combination of splicing and collapsing. You see? Do you see what we're saying there? All right, but it's doable with splicing and splitting, and okay, with split up and split down and splice. It's doable, but it's not just a single one. I mean, going this way, it's just not a single one. But you can use combinations of ones. Can you see how you would do it? How you would go from the middle bottom in part B? How you go from the middle bottom to the left bottom? What would you do?
Splice the 40.
Yeah, there's a couple ways to do it, I guess. I mean, you could collapse the 40 and the 60 and the 70, and then you could splice the 50 in it, or you could splice the 50 into the right of 40 and then collapse that with the 60 and the 70. You see what we're saying? But anyway, it's doable. Now, what I'm saying is it's doable. You collapse the splash, that's doable. All right? So we'll just, like I say, the actual code for doing this is it's C++ and it's very, there's just a lot of C++ stuff in there and it's hard, can be hard to follow, yeah. But anyways, does everybody see how that works? Okay, now we're going to start with insertion. Okay, so this is inserting into a Nguyen-Wong B-tree. And here's the whole idea. The way you insert, now when you insert a value, what do you have? You know that you have a value that you're going to want to put into the tree, right? So the easiest place to put a value in the tree is where? Okay, so the way it works is you know there is you have one value that you want to put in the tree. So what you do is you start at, it's got to be ordered, right? So you start at the root and you know if it's you can determine the particular child of the root where it needs to go, and then you can find the particular child of that root and you know it needs where it goes, and then eventually you get down to the what? To the bottom. And when you get to the bottom, that's when you know that you can put it in, because you've done the order, you've kept the order on the way down. Do you see what we're saying? You've kept the order on the way down. So finally, when you get it down to be a leaf, that's when you do the insert. Are you with me? That's when you do the insert. And then what happens is, by doing that insert, by going down and pushing it down all the way down, by doing that insert, what might happen? You're inserting, so you might reach the what? The size restriction, okay? And so if it's too big, what do? You lift up. You lift up and you lift up and you lift up. And each time you lift up, you maintain the invariant. So it's just one trip down, one trip up. You cannot believe what a great concept this is for inserting into a B tree. Now, this first little utility function is on this paper that I've handed out for the code, and so as we go through the figures, I handed this out so that we can refer to it, so I don't have to keep going back to the back and forth on the slides. And also this code, this pseudocode description of the insertion of the insert and remove you'll have this on the final exam, and you need to be able to trace insertion and deletion. Okay, so I'll just tell you right off the bat, this is what you need to be able to do this. All right, so here, the first one is, we're first going to take a look at this utility function called split up and apply. All right, so this is a utility function, and here's the pseudocode description of it is here. It says split up and apply, and the parameters are order and CMD, which stands for command. And the order, we know what the order of the tree is. That's, you give the order of the tree when you set it up the first time. Okay, that's fixed for the lifetime of the tree. The order is fixed. Okay, so split up and apply has order, and then CMD, which is a command. And the code is if size is greater than order. So what happens is, like maybe on the way, as stuff is moving up and down here, what happens is, if you lift a value up or you push a value down, if a node gets too big, then that split up and apply, it's the purpose of split up and apply is to fix that. It's a fix-up operation. So look at it's a simple if statement. If size is greater than order, that means the node is too big. And so where do you split up at? The middle. And if you split it up in the middle, if it's too full and you split it up in the middle, then those two, the left and the right that's left over, are you with me? They will satisfy that 1/2. Are you with me? There's the, you see what we're saying? They will satisfy that minimum 1/2. Is everybody clear on this? So there's the order invariant. Okay? And then what happens is, but that only happens if it's too big. So that only splits if the tree is too wide. And now this CMD, this is the functional paradigm. This is functional programming. Now, we did this before. We did this once before. Do you remember when we did the hash table? And we had the Knuth and the Bernstein hash functions? And what did we do? We passed those functions as a what? As a parameter. This is the same thing. This is the same thing. This CMD is a variable, but what is its type? It's a function. It's a variable whose it's a formal parameter. It's a variable whose type is a function. And so what happens is that function is either going to be a no-op, which means no operation. In other words, it means it does nothing. It's just a function with an empty body that just calls a function and returns and nothing happens. That's what we mean by no-op. Okay? And the only other possibility that we're going to call it with is a splice. It's either going to be either a no-op or a splice. All right? So that is split up and apply. And that's a utility function that we're going to use. Okay? And now, here is the code for inserting into a Nguyen-Wong B-tree. So check this out. So what do we want to insert into a tree? We want to insert a value. So that's the key. So like if we want to insert 60 into the tree, then key is 60. And then order is the order of the tree, which is set up at that's fixed for the tree, right? And now look at this code. If tree is empty, what do? We create a new single node temp tree, and for this we use the constructor where we give it a value, so that with the key value, are you with me? And then we splice at 0 temp. Now are you with me on that? We splice at position 0, the empty tree, so we're splicing it into the empty tree. Yeah? And then we return. That's it. That's all there is to do. So that's inserting into an empty root. Else what do? Else we call in helper, and now we have 3 parameters: key, order, and the no-op lambda command. Now what do we mean by this? Well, in this example, the first parameter is the key value that we're trying to insert. The second one is the order of the tree, which is fixed once and for all for the lifetime of the tree. And the third one is that command. This is a function. This is a parameter whose type is a function, and we are giving it the no-op command, the function that does nothing. Yeah, you'll see why. We'll see why in a minute. So that's else call in helper, right? So to recap now, what we have is a split up and apply utility function. We have the main insert, and it calls the helper. Now let's take a look at the helper. Now it's amazing that in these few lines of code, we are able to insert. I can't tell you how neat this is with these few lines of code to be able to understand how to insert into a B tree. This is amazing. Look at our in helper. Now you see we have key, order, and CMD. Now that CMD is the formal parameter. Let's go back to the previous. What was the actual parameter? No-op lambda. Are you with me? Is everybody clear? So in helper, key, order, command, and so that command, when it gets called from the original one, that command is the no-op. All right. Now before we kind of look at the ideas in going through here, let's take a look at what in helper calls. Do you see how this is recursive? This is in helper, and what does it call? No loops, no for statements, just one if, and what does it call? It calls what? Down here? Call underscore child sub k dot what? In helper, key, order, command. So this in helper is calling what? In helper, the next level down. Now, does everybody see that? In helper is calling in helper the next level down. And then what will that do? That will do some processing, and then what will it do? We'll call in helper the next level down, and it'll do some processing, and then what will it do? Call in helper the next, and until eventually it gets to what? The base case and so the one at the very bottom will execute what? If tree is empty. So we're inserting out a leaf. Now, is everybody clear on how that sequence of events works? On the way down, on the way down, on the way down, until we get to a leaf, right? So, all right, so let's assume that we've gotten all the way down, and we've gotten to the leaf. Okay, so if the tree is empty, so we're inserting at a leaf, what do? We create a new single node temp tree temp with key, and we execute what? Command on that temp, and then return. So, and then when we return, we're going back on the way back up. All right? Is everybody with me on this? All right? So now that's if the tree is empty. That's when we get all the way to the end, and then we return and we start going back. But what happens on these intermediate steps on the way down? What happens is, else. Now check this out. Determine k, the index for which data sub k equals key, or if key is not in this tree, the index of the child tree in which key should be inserted. What does all that mean? What all that means is this. If we are in, like here, this is sub 0, sub 1, sub 2, sub 3, sub 4, and this is 0, 1, 2, 3, 4, 5, and this is like 20, 40, 70, 80, 90. And if key is 50, what does that pseudocode description say to do? Determine k, the index for which what? Data sub k equals key? Does data sub k, do any of these data sub k's equal key? No. Okay, so what? Or, if key is not in this tree, the what? Index of the child tree in which key should be inserted. So, it's not here. So, what? So this would imply what for a value of k? 2 is correct. Because why? Because the 50 is between 40 and 70, so it has to go down here. Now, is everybody, are you with me on this? So how would you do that? You'd have to do that in a loop, a while loop. And you got to be careful because, you know, it's a little tricky. You got to go through in a loop, and because it might be on the right, it could be to the left of the minimum or to the right of the maximum. So, you know, you got to just be careful how you write the loop so that works. But anyway, does everybody see that's the pseudocode description that k would be 2? Right? And now look, if k is less than size, all right, now what is the size of this? What is the value of size with this node right here? 5. So if k is less than what? 5. So if k is less than size, and data sub k equals key, so, you know, like if instead of this being 50, suppose this were like 80, then what would happen is k would be 3, but this 80 would equal this 80. And so if those keys are equal, then the duplicate keys are not allowed. So all we do is we just return at this point right off the bat. Okay, because we're trying to put something in. If this were a dictionary and we had a key value pair, then we would replace the values with that key. And the values were coming down too. Are you with me? So this is where we're doing this, treating this as if these were keys of a dictionary. All right? But now, if that's not the case, now look, you guys, this part is easy to understand. We just find out where this is. Now look, it's just 4 little lines of code, or 1, 2, 3, 4, 5 little lines of code. Watch this. Old command gets command. So what do you suppose old command is? It's a little temporary local variable, and we're saving the old function. Are you with me? So we're going to save that. So the old command gets the command. And what was command? Command was passed to us as a parameter, right? So old command gets command, and then what do? And then now our command. So now the new command gets what? splice at k. So what would the command, in this particular example, what would the command get? It would get what? Now, what would the command get? It would get splice at 2. Now, do you understand that we're creating a function called splice at 2? Now, why do we want to create a function called splice at 2? Because why? Because this 2 is this 2, and whenever we're going to, and to splice on the way back up, we want to splice it. We're saving it. We're telling it that we're going to splice that 2 on the way up. See? Okay, so does everybody see the mechanism there? I mean, what's happening there? We'll do a bunch of examples. We'll do 2 or 3 examples. Pretty soon it'll click. All right? So the command gets the splice at k lambda command, and we call what? And now here, what do we call? We call what? Child. So now this would we call what? Child sub what? Sub 2. Okay, and so that would be this one down here. Are you with me? Where this 50 needs to go. Are you with me? So it's going down. Yeah. And furthermore, what are we passing it? We're telling it to do what? What's the command that we're giving it? Splice at what? It says here. It says splice. Yeah, and in this particular example, it's what? Splice at 2. So when this guy is coming back up on the fix-up, what will it do? It will apply what? Splice at 2. See? Splice at 2. So we'll see how, why we are. But anyway, we're saving that splice at 2 operation because we're going down there. We need to splice at 2 on the way back up. All right? So it calls it. And then what does it do? It does the same thing. It calls, boom, and then come back up. And now when we're coming back up, now what do we do? So now we've done this, and it's gone down, it's come up, and now what do we do? Command gets what? The old command, which is the one what? That was given to us by our parent. We are restoring it. Are you with me? We are restoring that command that was given by our parent. And what do we do now? Just one more thing, what? Split up and apply with order and that command. And that's our little utility function. And that's the fix-up on the way up. And it's just that one fix-up on the way up. And that's our little utility function. All right, now this, I'm telling you, when I first saw this, I thought this can't be right. It can't be this simple. But it is conceptually a little tricky because we got this functional programming and everything. But still, I think it's, and the amazing thing is that removal is just as easy. It's very similar. Yeah. Did you have a question?
No.
I think maybe if we do a few examples, you'll see. Okay? So now, first of all, the examples that we're going to be doing are for an order 4 Nguyen-Wong B-tree. So here, let's do, so order 4. Now order 4 means how many data values? How many data values are allowed in a node?
Oh, between 0 to
Not 0.
is that the regular one? Is that
So 2, how many data values are allowed in a node?
2 to 3.
Between what and what? I mean, what are the possible values?
2 to 3.
2, 3, or 4 data values per node. Now, is everybody clear on that? Because between 4 and the order. 2, 3, and 4. Are you with me? Okay. So let's do several examples. So first, the tree has one non-full node at the root. So here's our initial tree. How many data values does it have? 3. So 2, 3, or 4. And what are we doing? We are going to insert 50. Or sorry, we're going to insert 30. Now, I don't want to have to go back to that code, so let's refer to our reference sheets here. Okay? So what's the first thing that happens? The tree, okay, so the tree is not empty, right? So we call the in helper. Are you with me? So we call the helper with the what? with the no-op command. Now, what I've done here in part B of the figure is I've just put a little indication, no-op. All right? Does everybody see? We put no-op, all right? There. Okay, so no-op is command. You know, that's the value of the parameter that gets called in the helper. Okay, so now, so we're calling the helper with, now what's the first statement in the helper? If what? Tree is empty. Is it empty?
Yes.
Wait, is this empty?
No.
No, it's not empty. Are you with me? We're here. Is everybody clear? So it's not empty. So what do we do? Else determine the what? It says determine what?
K.
K, the index for which blah, 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 blah. Okay, so now what would K be here? We're inserting 30, so what would K be? 1. Is everybody good on that? Because that's child sub 1 is between the 10 and the 50. So, and now what does it say? So we determine the K. Now what? If K is less than size and data, does data equal the key? No. So what do we go? So what happens? Old command gets what?
The command.
No.
Oh, yeah, gets the no-op. And the new command gets what?
Splice at 2 and 1.
Splice at 1 because K is 1. Now does everybody see that? Splice at 1. And now what do we call? Child sub what?
1.
No, I thought K was, oh yes, K is 1. Okay, so we call underscore child sub 1 dot what? In helper, key, order, and what for the command?
Splice.
Splice at 1. Now let's go back to the top of in helper. Now if, okay, I think we went at, so now we got called with splice at 1, all right, in part C of the figure, because K is equal to 1. Are you with me? Okay, so now let's go back to the top. In helper, if what? Is tree empty? Yes. Are you with me? So what happens? If tree is empty, so what do? Create a new what? A single node temp tree temp with key what? No. The key is 30, right? Are you with me? Okay, so the key with key 30. Now what does it say? With key 30. So here, create a single value 30 temp tree. Are you with me? And then what does it say? Execute. Now what does it say to execute? What does it say to execute? What's the command? What does it say to execute? Splice that 1 with what? With what tree?
So the 30 goes up?
Yes. So splice into the parent tree, right? So execute command temp. And boom. All right? So now we return back to where? We just did the call, so now what do we have to do? Command gets what? Old command. But now what? Now this command gets what?
Do nothing.
The no-op. And now what do we do? Call split up and apply order 4 with what? A no-op. So call split up and apply with the no-op command, and boom, there we are. Now, does everybody see how that worked? So boom, 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 up, 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 down, 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 push down, lift up. All right? Now, let's see how to grow a tree. Let's see how its level gets deeper. Now let's insert into an order for a Nguyen-Wong B-tree, and the tree has 1 full node at the root. All right, so here we go. Initial tree. Now, remember we said 2, 3, or 4 data values per node. This one now has what? 10, 30, 50, and 60. It's full. So initial tree, we want to insert 70. Are you with me? So let's just take a look at the code. What does it say? What's the first thing? If what? If tree is empty. Is it empty?
Nope.
No. So we call what? In helper with what? The no-op. Okay, so the no-op lambda. So there in part B of the figure, there's the no-op. Right? Okay? And then what's next? Determine the what? So then, okay, so determine the what? Wait, where are we?
Determine the K for the index.
Are we at determine the K, the index for which data sub K equals key, or if it's not in the tree, the index of the child which should be returned? Is that right? Yeah. Okay, so what's our value of K? It's going to be 4. Are you with me? Because it needs to be inserted down there at 4. Right? Okay. And then the old command gets command, and command gets what? Splice at 4, because K is 4. So that function gets splice at 4. That's the splice at 4 function. Right? We're at call child sub what? Sub 4 in helper key order command. Okay, so now when we call that, that's okay, so we call that. But now when we come back to in helper, if tree is empty, that is true. So now what do? We create a new single node temp tree with key and execute. And then what? Execute what? Command temp. So then what do we execute? Splice at 4. Now do you see why we had saved that splice at 4? That's going to be splice at 4 on the way up. And splice at 4, it needs to be spliced in there because that's where it belongs. Okay? So it's going to be called, and so splice at 4. And then we return, okay, and so now we have returned back to here, but now we have to finish our fix-up. And what is our fix-up? It's command gets old command, so the command gets no-op. But now what is it? Now what gets called on the fix-up? Called what? There on your code. What gets called? Split up and apply. Do you see? So when we do a split up and apply, we're going to split up, but what are we going to apply? The command. What's our command? No-op. Yeah. We're going to split up and apply. But split up, where's it going to... Okay, so... Oh, and by the way, where's our split up and apply? It says if size is greater than order, which it is, right? Because now 5 is greater than 4. But it says split up at what? Size divided by 2. What's size divided by 2? 5 divided by 2 is 2.5. The floor of that is 2. So it's going to split up at 2. So this is 0, 1, 2. That's the 50. Are you with me? And so it's going to split up. And then it's going to execute the command. But what's the command? No-op. So, boom. There it goes. And you see we got the size restriction. Right? It got too big by 1. So it just cuts it in half, splits up and by, and so now it's at the minimum. Okay, 2 in each child. It was 5, now it's 2 in each child. 5, which is 1 too big, 2 in each child.
And it's just the children that have to obey that rule?
Well, every node has to obey that rule except possibly the root. Except the root. Because the root has to, you have to be able to have the root be smaller. Because obviously if you have an order 4 tree, and you just have one item in it, it's going to be at the root, and you can't have at least 2 if there's only going to be 1 in there. You see what I'm saying? So the root is the exception to the rule. Yeah. Now, does everybody see how that worked? All right. Now, let's see what happens if you insert into an order 4 Nguyen-Wong B-tree, where the tree has children and a full root. Now watch this. This is really cool. So do you see, here we have the root is 17, 30, 42, 50, and we got 10, 15 to the left of 17, 20, 25 to the left of 30, 35, 40 between 30 and 42, 45, 47 between 42 and 50, and 55, 57, 60, and 70 is to the right of 50. And it's all ordered. Are you with me? And what about this restriction? 2, 3, or 4 data values per node. Are we good? Is it ordered? Is it balanced? It's balanced, it's ordered, it's got the node, we've got the node restrictions. Everybody good? Now look, we're going to insert 65. We're going to insert 65. Okay, so what happens? Insert, is the tree empty? No, so we call the helper with what? The no-op command, right? So okay, so what's the first thing that happens? We call the helper with the no-op command. So here we are, we're in the helper, boom, in part B, we're in the helper with the no-op command here. Right? We're in the helper with the no-op command here. And so now what does it say? Determine the what? K. So now what's K going to be if we are inserting 65? It's going to be, now we're up here, you realize we're up here. So it's going to be 0, 1, 2, 3, it's going to be what? 4. So K is going to equal 4. Are we good? So K is going to be equal to 4. If K is less than size and data equals to K, no. So what happens? Old command gets what? No op. And command gets what? Splice at what? 4. Because we just determined that K was 4. Splice at 4. All right, so here we go. So now we call the helper with splice at 4 command. So here we are down here, splice at 4. So there's the no op, there's a splice at 4. Call the helper with splice at 4 command. All right. So now what happens? Let's go back to the top then. Is the tree empty?
No.
No. So we don't blah blah. So determine the K. So now what's our K for here?
3.
3. 0, 1, 2, 3. Because 65 is between 60 and 70, and that is that child sub 3. Are you with me? Okay. So now our old command gets command. Command gets splice at, what was it? 3. And call what? Child sub 4, right? Sorry. What was K? 3. Child sub 3. 0, 1, 2, 3. So now we're going to call, boom, this one. We're going to go down to this one. Okay? So here. So now we are down here in part D of the figure. Call helper with splice at 3 command. So here we are at splice at 3. While we're getting to, you see how this works? Okay, splice at 3. And so now we go back to our code. Is helper, now if tree is empty. Is it empty? It is. So what do we do? Create a new single node temp tree temp with key what? That got passed down. What was the value? 65, right? 65? All right, so here. Create a new single value 65 temp tree like this, okay? All right, and then and from the previous figure, the command is splice at 3, right? So after we do that, we do and then we execute. And now, do you see up there on the if tree is empty? Now that we have created that, what does it say? Execute what? Splice at 3 on the way up. Are you with me? So it says splice at 3, so we splice at 3 on the way up. Okay, oops. So here we go, we spliced at 3 on the way up. But when we spliced at 3 on the way up, now what? Now we're back, now we have returned from the call on this. So what statements need to be executed now? Command gets old command and what? Call split up and apply. Are you with me? Command gets old command, we call split up and apply. Well look, so the old command is splice at 4. Alright? So we call split up and apply. Now, split up and apply, that was that utility function. It only executes if what? If what? It's too big. But is it? It is. It's 5. It's not 4. So it is too big. So split up and apply work actually does something. So what does it do? It does split up at what? 5 divided by 2, floor is 2. Right? So 0, 1, 2. Are you with me? So 0, 1, 2 here. Okay? So what goes up?
60.
The 60 goes up. Now can you see what's going to happen? The 60 is going to go. So look. So now the 6. So and it's let's go back here. Because the 60 goes up and it executes what? Splice at 4. So where's the 60 going to go up to? 0, 1, 2, 3, 4. So it's going to go up here. So the 60 is going to go up here, right? Because this splice at 4 was told us that when we executed it, it's at 4 here. Okay. So the 60 goes up to here. But now what? But now we are returning from this one. So let's go back to our return code here. What does it say? Command gets old command. So our old command is what? No op. And it says call split up and apply. So we call split up and apply. But now what? Does split up and apply do something in this case?
Yes.
Yes. So what does it do? It does split up what? Where? At size divided by 2, which is the what? The 42. Are you with me? Ah! And boom. I tell you guys, this, I mean, do you see how this is amazingly easy compared, you don't know how hairy the traditional implementation of the B-tree is. Okay? So that's how you see how this is how insertion in a B-tree works. Yeah, question.
Back on the previous one. So when we're
On part F of the figure.
Part F, yes. So we are calling split up and apply, and first we do split up at size over 2. So we're splitting up at the 60. Does that single command, does that put it up there, or does it just separate it?
Okay, what happens is the split up at size divided by, here, imagine this. I didn't actually do the individual ones. Yes. Yeah, I could have drawn more figures, intermediate steps. So what happens is the split up, so the 60 would go up and the 55 and the 57 would be here, and then the apply puts it up here and then they come back up. So I actually did not do a separate figure for the split up at size divided by 2 and a separate figure for execute command host. I combined those.
And
So it is in 2 steps.
the command that we're doing is splice.
It is splice at 4.
And when we do splice at 4, the children.
When we do splice at 4, the 60 gets spliced in at 4 up here.
Right, but the children of 60 get mushed?
No.
No.
No, look.
Oh, okay.
In part G.
Oh, okay. Yes.
Yeah, so it's actually in 2 steps. It's split up, so it's boom, and then splice and boom.
Okay.
But you see, look, don't you see that that's this? Look, let's go back to our very first slide here of the... Do you not see that is... So we are lifting the value up. That's in part A of this figure, you see. In fact, those are the 2 steps. So I'm combining this whole thing in 1 step in that figure. That's the point. That's the point of this.
Yeah.
Is to combine those those operations in. Yeah.
Yeah. Okay.
I tell you guys, this you don't realize. Anyway, you young whippersnappers. Anyway, good deal. See you tomorrow.